Hi, this is Analyzing Gephi Dynamic Network tutorial part 2. I can say this tutorial simulating the infection of the dynamic network object in R. So a little bit long time ago, I made a tutorial video about analyzing Gephi Dynamic Network part 1, and this tutorial is part 2. So if you didn't watch the previous tutorial, so part 1 and also the Gephi tutorial about the hospital contact data, you need to watch the previous tutorial videos. So today I'm gonna use EPI model to simulate the infection over the dynamic network object in R. So first of all, we need to understand ERGM and STERGM, and before move to EPI model. Okay, let's see what we've done and what we will do. At the very first tutorial, we visualized the hospital contact data by using Gephi. So we convert the data to Gephi format. So we make some very looking good network in Gephi. And next one was we analyzed the data of Gephi in R. So we convert CSV data to dynamic network object in R and analyzing the object in R. That is the last tutorial video. And finally today, ERGM, STERGM, and EPI model looks very difficult. So this tutorial will not cover exponential family random graph model at ERGM and separable temporal ERGM, STERGM, because for them I need to make lecture videos, not just simple tutorial videos. So I need to spend. I need to spend lots of time for them. So I don't think so I want to do that. So I just make tutorial videos for YouTube. I'm going to use EPI model and the observed network data we already have. But EPI model works on ERGM and STERGM. What does it mean? It sounds very confusing. I will not use ERGM and STERGM, but use only EPI model. But EPI model is using ERGM and STERGM. I need to use EPI model, but EPI model need to use ERGM and STERGM. But I don't want to use ERGM and STERGM. It's very, it's wordplay. So let me explain about it. ERGM is a sort of a categorical analysis like logit or probit. Look at here. P means probability. So probability of creating edge or link between two nodes. Here, EXP means exponential. So exponential means always positive. Yeah. So and data means is weight on G of Y. So what is G of Y? G of Y can be any network statistics like edges or triangles, some other things. any kinds of network statistics can be G of Y. And here, kappa of Y, it means every possible cases of G of Y. So it means it's from observed data, it can be every possible cases. So this is we can call probability, right? So this is the basic mathematical form of ERGM. So like linear regression models and logic models, we can fit the network data. It means we can get coefficients and test our null hypothesis. STERGM is an extension of ERGM for time series data. It means dynamic network. So S stands for separable. Something is separated. What is separated? STERGM contains two models. Yes, something is this one, right? So first model is formation. The second one is dissolution. Formation for creating formation for link or edges. Dissolution for edges or link. So STERGM can contain two ERGM. What does it mean? So over time, the edges or links can be created or can disappear. So the formation and dissolution can have different models, right? So can be have different mechanism. So they can have different two models or or same models. It depends on some data or the modeling methods. So this is called STERGM. Oh, let me see. Yeah, EPI model. So basically, EPI model run two kinds of simulations. First one is simulating networks based on the STERGM estimation. So from the STERGM estimation, EPI model simulated networks, right? And the second one, over the simulated networks, EPI model run another simulation for infection or epidemic process, right? So there are two different simulation in the EPI model. But I want to know the infection process on the hospital contact network data we have, not on the simulated one, right? So we don't need this first step. So that's why I said I'm not gonna use STERGM, right? So I will skip the first step of the EPI model. Instead, directly move to the second step with our observed network data. Okay, let's move to our section. So first of all, we need to load the library EPI model. Yeah, and we already created the dynamic network object in the previous tutorial. So I saved it. So just load it. Let's look the net. So this is our network dynamic object properties, and I need to change it. I will show you what I change it. Look at the vertex attributes. So here label. So I changed the label. So let's see what is in the label. In the label, we can see the MED, NURAD, MPAT. It means the position or the role of agent in the hospital. So MED means medical doctors, NUR means nurses, ADM refer to administrative staff, PAT means patients, right? So as I explained, we need to move to the second step. We will we will skip the first step, right? So for this one, we need to update some modules in the EPI model. So it sounds like difficult, but don't worry about that because you'll go to this website, this EPI website. There is some example to change modules. So modeling epidemics over observed networks. So you can see, go to here, more modules, and there is a code for changing module here. So basically, this change is same as this example, but a little bit different. I will explain what I changed here. Look at here. This is our first module for initialization. The new name is AnyNet INIT mode. So move here. So I added some dynamic vertex attribute. It is called T status because I want to track. I want to know the the dynamic patterns of infection over time. So it this vertex, a dynamic vertex attribute will say about that. And then next module is infection module. Here the new name is my.nif.mod, and then go down. Here also I added T status with same reason. Okay, so next one. Here, so INF PROB means infection probability. So in this code, I just set 0.1. So it's not so high, not so small. It's just 0.1. Next one is INI, NUM is 1. It means at the very beginning stage, very beginning time step, the only one person will get infected. So only one person. So if you want more, you can change 2 or 3 or 10, whatever. But I so in this model, I just set just number 1. And this is parameter is also the function of EPI model param.net. It is about infection probability. So here is matching, and then next function is initnet. It's about initial number. So here, so this is so, and then move to next one. So controllet is for combining functions the epidemic model needs. So first of all, the type SI means susceptible infection model. So our time duration is from Monday to Friday. It's not too long for recovery. So I don't think SIR model is good for our data. So just I put the SI. So it means I want to know infection process. in the dynamic network. N steps. So it is for time step. Uh, our time step is 17,377. So one step is 20 seconds. So we in the previous tutorial I convert 20 seconds to one step. If you want to know about that process, just move to the previous tutorial. And n sims is number of simulation is just 5 because look at this time step. We have long time steps. So even it's number 5, it will take long time. But yeah, so just I put the 5. I just put 5 to save time. Initialize function and infection function we already changed and make the module our module. So put the changed module here and here. And module order, yeah, the first one is infection, so run infection function, and the next one is make final statistical output or numbers. And okay, let's run a simulation. Just a moment. Yeah, this net sim means the second step of simulation in EPI model. So this net is our network data is PARM in here, INIT from here, contours from here. So let's run. Yeah, it will take a long time. As you can see, our time step is 17,377, and then we need to run these time steps for 5 times. So we need much time. So I just stop it. I already ran the simulation, and then I saved it. Just load the data, and let's see. So wait, okay. In the first plot, show us the pattern of number of infected or the number of the susceptible. Look at here. This number of impacted people is increased, and then finally is more than this susceptible line. And this is incidence. Okay, we can see the pattern of infection, right? And then we also want to know about the infection process in the network, right? So for this one, we will use plot time network, and this is time at 1 means the beginning time step, at the very beginning time step, and then next one is 2160 60, it means 12 hours. So first plot will be for 1 p.m. Monday, next one is 1 a.m. Tuesday, next one is 1 p.m. Tuesday, and keep going, and the last one is 1 a.m. Friday. So let's just see what happened. So let's wait. Okay. Oh no, sorry. Okay, let's see. So as you can see, the at the initial time step, there's only one person got infected, and then over time it spread, and then 1 a.m. on Friday, so most of all people got infected. So we can see the pattern or some pattern of spread of the disease. Okay. The next step will be simulation by roles. So as I mentioned, we have 4 kinds of agents: administrative staff, medical doctors, nurses, patients. Administrative staff, 8 people, 11 medical doctors, 27 nurses, 29 patients. So our assumption is our basic setting is the at the at the initial time step, only one person got infected, right? So how about the one person is administrative staff? So how about one of the medical doctor got infected at the initial stage? How about nurse? How about patient? It probably very uh, different infection events can happen by who was the first infected person. So let's try to simulate uh, each cases. So administrative staff, medical doctor, nurses, and patient. So it can be helpful to making a policy to prevent uh, the hospital infection, right? So, you know, sometimes we need some different policies for target. So maybe maybe we can make some the policy for when the first step when doctors when medical doctor got infected. Maybe we can have some different policy when a patient got infected. So maybe we can think about lots of options. For this, we need to update. We need to change something. Just here. Mm, look at here. So I make some uh, this administrative staff vector, and this vector for medical doctors is vector for nurse, is vector for patient, and then this as you can see, this is one of administrative will get infected at the initial stage. And next one is medical doctor, next one is nurse, next one patient. So we need to learn one by one. So first one is run with this one, next one run with this one, like here, and then third one is learn by this code, and then the lastly we run the simulation with this one. Okay, and then the others will be same. Okay, so other same, we just put and we run this one. So this one simulation for administrative step, this one for simulation for medical doctor, this one simulation for nurse, this one simulation for patient. So I already run the simulation because it takes a long time. So let's see. Oh, sorry, where is it? Okay, let's Let's see. Yeah. So we can see the big variation here because our simulation is just uh, simulation number is just 5. So if we will run maybe 100 or 1000, we can be better. But at the same time, it can be very the for administrative staff, it can be very various cases, various infection cases can happen. We can think about that. And the next one is medical doctor. Let's run. Not run, just to load. If you run this one, it takes very long time. It's a medical one, medical doctors case. Yeah, we can see with a different pattern, right? And then for nurse, yeah, also different pattern. But you can see the variation is very narrow. It means usually a very consistent result from simulation. Next one is for patient. Yes, it's like nurse. It's also narrow variation, right? So you get the instance. Mhm. So let's compare all of them. Mm, mm, yes, this for administrative staff. This for medical doctor. So even though we run 5 simulations, but we can see the patterns, also some what kind of variation. So look at here, the variation is very big. Here, so the initial steps, in the first 5,000 steps, there's not so much variation, but and the second half of time, this variation is very big. So medical doctors and nurses very different from medical doctors and administrative, and also narrow variation. And patient, mm, yeah, it's similar to nurse, right? It's a nurse pattern. Pattern of nurse and patients looks similar. And then they are very different. So we can see the different pattern of infection in this from the hospital contact network data. Okay, this is the end of tutorial. So see you later. Thank you.